For centuries, the simple idea of floating above the Earth in a balloon has captured our imagination. It remains one of humanity's oldest aviation concepts. But the early history of lighter-than-air flight is a record of extreme fragility. In 1897, a team of 3 Swedish adventurers attempted to cross the North Pole in a hydrogen balloon, a journey that ended in their deaths after Arctic conditions grounded their craft. 40 years later, the Hindenburg disaster visually cemented the flammability and structural weakness of these early vehicles into the public consciousness. These dangers persisted into the modern era. In 2011, a Goodyear blimp caught fire and crashed in Germany, taking the life of its pilot. This century-long streak of failures eventually pushed airships out of serious aviation and into the realm of mere novelties. For decades, the industry operated under a consensus that the technology was too unsafe for heavy use. To understand why these craft fail, we have to look at the load exchange challenge. When an airship drops a payload, it suddenly loses massive downward weight, pitching upward out of control. This anomaly caused the 2011 crash. As passengers jumped to escape a fire, the sudden weight loss forced the craft to violently destabilize. Today, we have a logistical problem that requires this kind of heavy lift hovering. Transporting infrastructure into remote territories, like the Australian outback, currently requires building terrestrial road networks that cost billions of dollars and generate significant carbon emissions. Modern supply chains require a zero-emissions, heavy-lift cargo ship, but historical lighter-than-air designs were physically incapable of doing the job safely. Aerospace firms are now rebuilding these vehicles using the chemistry of advanced materials. The fragile historical canvas that used to tear and burn is being replaced by the rigid, interlocking bonds of carbon fiber. Engineers are integrating titanium and Kevlar into the structural skeletons, creating hulls designed to withstand atmospheric stress for up to 40 years. Inside these hulls, LiDAR sensors use lasers to measure distances and calculate internal helium volumes in real time, allowing for constant aerodynamic stabilization. The combustion engines of the past are being replaced by electric systems. LTA Research is outfitting their craft with arrays of 12 independently rotating electric motors powered by solar panels and batteries. By combining high-tensile carbon polymers with active digital stabilization and electric propulsion, developers are addressing the structural weaknesses that plagued previous generations. Modern hull design doesn't solve the load exchange physics on its own. To address that, Flying Whales developed the LAC-60T. This cutaway shows a simultaneous water ballast system. As cargo is winched out, water is pumped into the ship at the exact same rate, keeping the total weight constant. To prevent sloshing, internal tanks feature grid-like baffle walls that lock the liquid into compartmentalized cubes. Alternatively, AT2 Aerospace uses an aerodynamic hull shape and an air-cushioned hovercraft landing system. This allows the massive airship to stay securely settled on snow, water, or sand while dropping its heavy payload. Through the use of fluid dynamics and hovercraft technology, engineers have developed mechanical solutions for the load exchange problem that previously limited the industry. With these updates to ballast and material strength, the industry is shifting the classification of these vehicles from blimps to specialized flying cranes. Looking at the skeletal framework of this massive airship hangar proves the scale of these new projects. This is an industrial aerospace endeavor aimed at high-capacity transport. The Skylifter project features a saucer-shaped design engineered to lift 150 tons across 2,000 kilometers of the Australian outback, bypassing the need for ground-based infrastructure. Companies like Flying Whales are currently working with governments to deploy a fleet of 160 airships across 22 countries to decarbonize freight transport. By swapping flammable gas and fragile skins for carbon fiber, LiDAR, and automated ballast systems, engineers have provided a technical path away from the industry's historical failures. If these current rollouts succeed, they offer a way to connect remote regions without the environmental cost of traditional